All right, folks, we will get started. We didn't quite finish the last section, so I just want to do a couple of graphs of cotangent for you. It's just like tangent, same tricks, but you just start off with cotangent instead of tangent. So cotangent, all right, instead of being over here and looking like that, like tangent does, tangent was between 0 and pi, and it was kind of backwards, right? That's your base cotangent function. Okay, so halfway between 0 and pi is pi over 2. Halfway between that is pi over 4. And you get 1 there. So we have these key points. All right, so that's cotangent, regular old cotangent. But we have a couple of mods here. So the period for tangent and cotangent is always pi over b instead of 2 pi over b. So it's pi over 4. The period's pi over 4, so instead of being from 0 to pi, it's going to be from 0 to pi over 4. Makes this halfway between those, and this halfway between those. And then this 3 here has made it 3 times as tall, so instead of getting 1 right here, we're going to get 3 right there. And then, of course, it repeats itself over and over and over again, right? That's it. Yeah. Oh, hell. Okay. There we go. Both. I want both. Both. I guess that bulb's blown. Anyhow, it's over here. So all we did was take cotangent and we adjusted its period. We got compressed by a factor of 4, and then we stretched it vertically by a factor of 3. That's it. Let's look at one that's a little more complicated. So this one, they did a whole bunch of stuff to it, all right? These are the hard ones, okay? So normally cotangent would look like this, right? And we'd want to know where these points went, right? This would be at pi over 2, and this would be at pi over 4. This would give you 1. That's regular old cotangent, right? And this is pi. Okay, well, this guy, I don't want to just be like, right, like that, because we have a shift here. Because of that shift, I don't know. Let me make my lines a little straighter here. Pretty, okay, straighter than that. Okay, I don't know if my vertical asymptote is going to be right here at 0 because there's a shift. So first off, let's figure out what our period and our shift are going to be. The period is always pi over b, and b here is pi over 8. 1 divided by an eighth is 8, so we have a period of 8. And then our phase shift is going to be to the right, and it's always c over b. It's pi over 2 divided by pi over 8. So 8 over 2 is 4. So this dude is shifted to the right by 4. So instead of putting asymptotes here, they got to get shifted over. Okay, so what used to be here is now shifted to the right by 4. Okay, this guy. It has a period of 8. So 4 plus 8 is 12. So there's where my asymptotes got moved to. Okay, I dealt with the period. From here to here is 8. And it's shifted to the right by 4. So that means, let's see, right here in the middle between 4 and 12 would be 8, right? So it would look something like this. Let's see, this would be a 6, and we would get a 1 here. But that's not quite the case, right? We do want to track what happens to this point and this point, because we still have to deal with that and that. All I did is deal with those 2 numbers. Okay, so dealing with this first, right? This would be a 4 here instead of a 1, okay? But now we need to shift everything down by 2. So I'm going to keep this guy as a reference. But if I shift everything down by 2, it'll look more like that. So this point got moved down there. That key point is now 8 minus 2 instead of 8, 0. And this point, since it got shifted down 2, is going to be at 6, 2 instead of 6, 4. Okay, so we just followed where those two key points go, right? We want to know where this one goes and where this one goes, right? Difference between those, that gives you your A. That's how you get the A. That's why you need 2 points to get the vertical stretch. And this guy told you your shift and your period, right? Okay, so one of them tells you how far it goes left or right, and it tells you how far it goes up or down. But this guy, you have to have a second point labeled so you can tell vertical stretching. So you always want to follow those 2 key points when you're doing tangent or cotangent, all right? Just for cotangent, you just start off with this instead of that and see what happens to it. And then, of course, it repeats over and over again, something like that, okay? So that's the last of last week. This week is season 6, right? So we are in, there we go, not that one. There we go. Module 6. Boom, module 6. So this week we have 2 sections, 6.3, 7.1. So there's 2 web work homework assignments. And then there's a practice writing assignment. That's it. So if we finish covering the material in class by Friday, we might have time to do some of this practice writing assignment in class. It'd be cool if we could. But so 6.3, here's 6.3. Our goal here is to start dealing with inverses, right? Just like you have sine, cosine, tangent, we need to have sine, cosine, tangent, inverse, right? Because what if I have, like, say, a right triangle, and it'll be like 3, 4, 5. Here's an angle. Let's say I know 2 out of 3 sides. What's the angle? I don't know. I know that tangent of the angle would be 3/4, right? But what's the angle? I need a function that'll undo this function. I need a tangent inverse. Is what I need. So those will undo one another, and theta will just be tangent inverse of 3/4. Okay, so that's the whole point of today is inverses. Okay, and we're gonna have to do some restrictions here. So what we want is some basic stuff like this. I mean, first off, sine inverse, this is not 1 over sine, okay? Remember, F inverse is not 1 over F, right? It means F inverse, okay? Sine inverse, this is the same thing as saying arc sine or a sine. Your calculator may have any one of these 3 buttons. They all mean the same thing, okay? So arc sine existed before inverse functions existed. It just happens to be that's the inverse of sine, okay? So that's the first thing you need to know. The other thing, so think about this. Remember x squared does not pass the horizontal line test. It is not invertible, right? But if we throw that away, then this dude is invertible here. And to get an inverse, right, the graph, if you flip over the line y equals x, that's switching your x's for y's, your y's for x's. That switches your domain and your range, and you would get square root of x. So x squared is invertible if you restrict yourself to just the right half of the graph, right? If you don't do that, if you have any of this, then this goes down here, and that's not a function, right? A function, one number in, one number comes out. So sine, cosine, and tangent, we have to restrict our domains to define the inverse here. So what do I have here? Here's some stuff. So sine of pi over 6 is a half. That means sine inverse of half is pi over 6. So we like to think of the numbers that go into sine and cosine as being angles, right? And then it spits out some number between -1 and 1. Well, we like to think of the numbers that come out of the inverses as being angles then, right? If an angle goes into sine, it's an angle that comes out of sine inverse. I mean, they're all technically just numbers. It's just how we're interpreting them, okay? All right, so you just flip it, right? Tangent inverse of 1 is pi over 4 because tangent of pi over 4 is 1. That's the whole point. We need these functions to undo whatever sine or cosine and tangent do. We want them to undo it, right? Remember the whole point of an inverse is to give us our x back. That's the goal, right? But there's some issues. So like if I did the square root of -2 squared, this is 2, not -2, right? So because we have a restricted domain, you don't always get the same number back. You see what I mean? You get a candidate basically, right? So sine, what does sine look like? It looks like this, right? Here's sine. So let's say I give you this x value, right? That's not a very good one. Yeah, fine. Sine is going to be like, boom, that guy, right? But if I give this to sine inverse, it's going to be like, it could have come from here. Oh, wait, it could have come from here. It could have come from here. There's an infinite number of choices to come from, right? It's like, well, which one did it come from? This guy or this guy, right? There's an infinite number of choices. This dude does not pass the horizontal line test, so it's not invertible. So what we're going to do is just pick a piece of it that we like. In fact, we're going to pick this piece because it covers the whole -1 to 1. We'll just pick that piece of sine. Passes the horizontal line test, therefore it's invertible. Okay, so let's look at that in more detail here. Let's get a little picture going on. Here. Draw it bigger. All right, bigger. Bigger is better. So sine looks like this. So I'm going to tell you same thing I just told you, but louder. Okay. So sine looks like that. But if I give you that x, sine spits out that y. Going backwards, if I give you this y, did it come from here? Did it come from here? Did it come from here? Could have come from an infinite number of them. But we want sine inverse to be a function. So we're going to fixate on the -π/2 to π/2. This is the restricted part of sine that we're going to define the inverse off of. You see, it goes all the way from -1 to 1. So if you give me any number between here and here, I will give you exactly one number back. Right? If you give me this number here, sine inverse will give you that number back. All right. So sine inverse always spits out something between -π/2 and π/2. Okay. Always. If you think about it on the unit circle, that's the right half of the unit circle. When I say the right half of the unit circle, I don't mean this angle. No, I mean this angle. It's always an angle on the right side of the unit circle. Sine inverse always gives you something on the right side of the circle. All right, -π/2 to π/2. Okay, that's what we're going to build our inverse after. Cosine is an even function instead of an odd function. All right, so here's cosine. Cosine looks like this. Right, does not pass the horizontal line test. So what we do is we throw away everything but this part from 0 to pi, right? 0 to pi, it covers the whole range, the -1 to 1. So for cosine inverse, if you give me that y value, cosine inverse is going to be like it came from this x value, something between 0 and pi, okay? So this is our restricted piece of cosine that we're going to build the inverse after. Cosine inverse always gives us something between 0 and pi. That's the top half of the circle, okay? That's what we're going to build our inverse after. And tangent. Tangent's kind of cool because it goes forever up and down, right? So tangent really looks like this, right? So if you give me something that came out of tangent, it could have come from here, it could have come from here, it could have come from here, right? We're going to throw away all this other stuff, and we're just going to fixate on this piece that's between -π/2 and π/2, our principal period. You can give me any number, right? This thing goes all the way up to infinity and down to -infinity. Give me any number you want. I'm with tangent inverse is going to say it came from that one. That's the one. Might not be true, but it's going to be the candidate, right? Okay, that's where it's going to say that it came from. So those, so tangent inverse always spits out something between minus pi over 2 and pi over 2. Notice we have round brackets here. It can't give us a pi and minus pi over 2. There's an asymptote here, right? Tangent of minus pi over 2 is undefined, right? So round brackets. So where is that? Well, that's the right half of the circle. So in summary, we have sine and tangent and cosine, right? Right half of the circle, right half of the circle, top half of the circle, right? These are the odd functions. This one's an even function, and that's why, okay? These dudes are symmetric about the origin. Okay, so domains and ranges. So let's think about domains and ranges. Domains and ranges. You can plug in any number you want into sine, right? And it spits out something between minus 1 and 1. Well, this is exactly what sine inverse is designed to deal with. Whatever can come out of sine, that's what sine inverse deals with. And it tries to return it back over here, but there's an infinite number of choices. So what it does is it picks the one choice that's between minus pi over 2 and pi over 2. All right. So if it was a perfect inverse, it would just be a circle, right? But it's not. We have to restrict it. Cosine, you can plug in any number you want to cosine, and it also spits out something between minus 1 and 1. Cosine inverse is invented to clean up after cosine. And it would like to give you back the number it came from originally, but there's an infinite number of choices, so it's going to give you back the one that's between 0 and pi, the one on the top half of the circle. Again, sine is the right half of the circle. Now, what about tangent? All right, well, tangent, we'd like to plug in any number we want, but we know we can't, right? Remember, tangent, these angles don't fly. You can't plug those angles into tangent. Tangent is the ratio of y to x, right? And x is 0 here. So tangent, you can plug in any number you want except for pi over 2, or any angle that points in the same direction. Pi over 2, this is pi over 2. See, I'm saying add multiples of pi. If I add pi to pi over 2, I'm pointing down. If I add another pi, I'm pointing up. Add another pi. You add multiples of pi to pi over 2. Those are all angles you cannot plug into tangent. So I'm saying any real number except for the angles that point up and down. Those are what can go into tangent, right? That's why we have the horizontal asymptotes. Tangent's pi periodic. Add pi to a number it can't accept, and you get another number it can't accept. So that's what tangent can handle, and tangent spits out something between minus infinity and infinity. Remember, its graph goes forever up and down. Well, that's what tangent inverse is designed to deal with, okay? Tangent inverse needs to be able to clean up after tangent. Well, tangent inverse would like to give us back the original number, but there's an infinite number of choices. So it always gives us the one that's between minus pi over 2 and pi over 2. Again, the angle on the right side of the circle, the unit circle. Got it? These are definitions, right? So basically all you have to remember right now is what comes out of sine inverse is this. What comes out of cosine inverse is this, and what comes out of tangent is this. Basically, that. Sine and tangent, right half of the unit circle. Cosine, top half of the unit circle. That has to be memorized because that's definition. That's how we've defined our inverses. There was an infinite number of choices. We picked one. Okay, so. Okay, what about the graphs? We know what the graph of sine looks like. What does the graph of sine inverse looks like? Right, well, I done told you, like, I'll do it again, right? Here's x squared. We threw that away. Here's what y equals x. When you flip over this line, you get this guy. So you just flip over the line y equals x. The domains and the ranges switch, okay? So again, here's sine. Let me make this smaller for a second. Sine looks like this, right? If I flipped it over the line y equals x, I would get this. It just go forever. That wiggly line to the left and right, that is sine. It would be the wiggly line Same thing, but going up and down, but that's not a function, doesn't pass the vertical line test. So what we do is we restrict, all right, we're going to restrict our piece of sine that we're interested in, right? We're going to restrict it minus pi over 2 and pi over 2, okay? And what's coming out here is between 1 and minus 1. So if we just fixate on this piece of sine and you flip it over the line y equals x, you get this guy, sine inverse, right? So sine restricted between minus pi over 2, that's the restricted domain. It becomes the range. The old range, minus 1 to 1, becomes the domain. So let's draw these separately, all right? Here's what sine looks like. So here's sine, the restricted portion of it, okay? Between 1 and minus 1. There's the restricted piece of sine. So now for sine inverse, instead of the range being 1 to minus 1, the domain is minus 1 to 1. And instead of the domain being minus pi over 2 to pi over 2, the range is minus pi over 2 to pi over 2. And it looks like this. It's that, but flipped over that diagonal. So this is the entire graph of sine inverse. That's the whole thing. It's just that little piece. Again, if we kept going, it wouldn't be a function. Okay, that's what the graph of sine inverse looks like. Range became domain, domain became the range. All right, that's the whole point of the inverse. All right, so that's sine. Here is cosine. Okay, so again, for cosine, cosine goes on forever and ever and ever. If we simply flipped it over the diagonal, we would get this, and that wouldn't be a function. So we have to restrict it. So we threw away all the rest of that, and we just focus on the piece that's between 0 and pi. That always spits out something between 1 and minus 1, okay? If you flip that over the line y equals x, you get this guy. 0 to pi is the domain, becomes 0 to pi is the range. Let's draw this bigger. So here's cosine. We're fixating on just this piece that goes to pi, 0 to pi, because it covers the full range, 1 to minus 1, okay? So we take that dude and we want our inverse. We just flip it over this line, boop. So 0 to pi used to be our domain. 0 to pi is now our range. Minus 1 to 1 used to be our range. Minus 1 to 1 is now our domain. And this guy looks like that. So I can give it anything between minus 1 and 1, and it's going to spit out one number between 0 and pi. All right. Minus 1 to 1, minus 1 to 1. 0 to pi, 0 to pi. All right, if we kept going, it wouldn't be a function. So we have to cut it off. Now it's a function. And now for tangent. There we go. All right, here is tangent. So tangent really, let's see, minus pi over 2 and pi over 2. We really have these asymptotes here. This thing goes forever up and down, but it repeats itself over and over again. But the problem is if I give you a y value and ask where it came from, there's an infinite number of choices, right? So what we do is we throw away all of that. Oops, not that. We want to keep that part. We throw away all of tangent except for its principal period here between minus pi over 2 and pi over 2. We just keep this piece of tangent, only that tangent. So you have something that looks like this. If you flip it over the line y equals x, you end up with something that looks like that. If we kept all the other periods, we would have this going on. We can't have that, not a function. So we threw away all the other wavelengths, right? We threw away this guy and this guy, because if we kept them, those would end up here and here, and that wouldn't work out. So we're fixated between minus pi over 2 and pi over 2. Let's try drawing them separately, just so you get, it's nice to see things separately. Minus pi over 2, pi over 2. We have these asymptotes. Tangent goes wah, right? Okay, it goes all the way up to infinity and down to minus infinity. There's your tangent, the restricted tangent. So tangent inverse, okay, the domain was minus pi over 2, pi over 2. So here, the range is minus pi over 2, pi over 2. You used to have vertical asymptotes. These become horizontal asymptotes. When you flip it over the line, y equals x, right? And so our range was minus infinity to infinity. So now our domain is minus infinity to infinity. So that's what your tangent inverse looks like. Tangent inverse, okay? Minus pi over 2 to pi over 2, the right side of the unit circle, right? Again, the right side of the unit circle. Cosine inverse, 0 to pi, top half of the unit circle. Sine inverse, minus pi over 2 to pi over 2, the right side of the unit circle, right? Angles come out of the inverse trig function because angles go in to our trig function. So we're just doing trig backwards, that's all. There's some subtleties though, we have to be careful. This one here is pretty easy. Where's this angle, 5 pi over 12? It's up here, right? 6 pi over 12 would be straight up, right? So because this angle is between minus pi over 2 and pi over 2, I can simply say that sine inverse of whatever this number here is that came out is approximately 5 pi over 12. So I just switched. I took sine inverse of both sides. Those undo one another, right? And they perfectly undo one another because this is something that can come out of sine. It's on the right side of the unit circle here. We'll do another one here. All right, cosine of 0.5. Well, we're treating that like an angle, right? Where is 0.5 in radians? Well, there's 0. Straight up is pi over 2, right? Pi is about 3. So 3 divided by 2. Straight up is around 1.5. So an angle of 0.5 is somewhere over here, right? That's an angle that can come out of cosine inverse. Cosine inverse always gives you something between 0 and pi. So since that is between 0 and pi, I could simply say, well, cosine inverse of whatever this is approximately 0.5. All right, just going backwards. Boop. Okay, just like cosine of pi over 6 is root 3 over 2. I could say cosine inverse of root 3 over 2 is pi over 6. Right? Where is pi over 6? It's right here. But what if I did cosine of negative pi over 6? Let's do a whole bunch of them. Cosine of pi over 6 is the same thing as cosine of negative pi over 6, which is the same thing as cosine of what is this, 11 pi's over 6, which is the same thing as cosine of 13 pi's over 6. These are all equal to root 3 over 2, right? But cosine inverse of root 3 over 2, it can't give you an infinite number of outputs. It can't give you an infinite number of answers. It has to give you that one. We defined it to be that way. There can only be one choice, right? So really this is like a candidate, right? We defined the inverse to always give us the one that is up here, and that's the one. So it's kind of a candidate for all the rest of these, if you will, all right? Because we like our inverses to be perfect inverses. We want this, f inverse of f, we want it to be that. We always want to get our number back, but it's just not the case, right? Because this function's not invertible, right? So this is our candidate. That's what the cosine inverse is going to give us. Think of it as a candidate for an infinite number of possibilities, all of which cosine of these give us the same output, okay? All right, let's do some examples. So how do we do this backwards? Okay, well, here we're looking at inverse functions. These are all inverses. So sine is the y value on the unit circle, right? So if I'm going to do this in my head, right, I'm thinking about the unit circle. I think about that as a y coordinate. Here is the line y equals 1/2. Every single one of those points on that line has a y value of 1/2. So sine of this angle or sine of that angle gives me a half. And it's a terrible drawing. I should kind of maybe draw it more like the scale, right? A half. So you can see the possible angles would be this one or that one. Sine of all those angles is a half. Sine inverse always gives us the one that's over here. So it has to give us the pi over 6. That's the one. It's not going to give us 5 pi over 6. Okay? It's not designed to do that. Sine inverse of negative root 2 over 2. Okay, well, I draw my unit circle. I treat this as a y value. Here's y equal, no, negative. I need to move it down. Negative root 2 over 2. So the possible angles would be like these or these. But sine inverse always gives me the one that's over here. And I don't mean this one. I mean this one. Negative pi over 4. Okay? It's that one and only that one. Now we're dealing with cosine. Well, cosine is the x coordinate on the unit circle, right? So I'll treat this as an x coordinate. Here's the line where all the x values are negative root 3 over 2. So our angles of interest would be these and these, but cosine inverse only gives us one. It always gives us the one up here. And I don't mean this angle or this angle. I mean this one, the one that's between 0 and pi. So that would be 5 pi over 6, right? Tangent is the ratio of y to x on the unit circle. So where's the ratio of y to x? 1, here and here, right? Pi over 4 and 5 pi over 4. Tangent inverse always gives us the angle on the right side. It's always the one between minus pi over 2 or pi over 2. So I don't mean that angle. I mean this one. So this is simply pi over 4. Okay? So that pi over 4, y and x are the same. So the ratio of y to x would be 1. By now, you need to have your unit circle down in your head. You need to be able to navigate it. Okay? If you're still like, I don't know where 5 pi over 6 is, you're way behind. Right? You need to know where those are immediately. Look at some more here. All right, a sine inverse. We treat this like a y value. So on the unit circle, here's the line y equals -1. So we really only have any angle that points in that direction. Well, sine inverse always gives me this one. It's not going to give me that one. It's going to give me a minus pi over 2. Okay. Tangent. Tangent is y over x. So where is y and x equal but opposite? Over here and over here. Tangent of those angles is -1, right? What is this coordinate? Minus root 2 over 2, root 2 over 2, right? If I do that over that, I get a -1. Okay, so the tangent inverse is not going to give me this one. Tangent inverse always gives me the one that's over here. This would be minus pi over 4. Cosine inverse of minus 1. Cosine is the x value. So here is the line x equals minus 1. So we have this angle. We're not going to give it that one. Cosine inverse always gives me the one that's on the top half, the one that's between 0 and pi. Here's another cosine. So here's my unit circle. Cosine is the x value. Let's see, here's all the x values of a half. So which one is it? Well, cosine's always the one on the top. Cosine inverse, I should say, always gives you the one up here. So this would be pi over 3. Okay. We're just doing trig backwards, but we have to restrict it to the domains that we specified, right? I'll tell you again. Cosine, top half. Sine, right half. Tangent, right half, right? 0 to pi, minus pi over 2 to pi over 2, and minus pi over 2, pi over 2. Round brackets, because tangent can never, okay? Using a calculator. Use your calculator. I'm going to say about that. All right. So I already mentioned this earlier. If you know 2 out of 3 sides, you can figure out what the angle is. Oh, there we go. So here we go. Here's a triangle. All they give us is 2 numbers. What's the angle? Well, let's see. We know what the adjacent and the hypotenuse is. Well, cosine is the adjacent over the hypotenuse by definition. So that means the angle has to be cosine inverse of this. And we don't have to worry about this guy spitting out an angle that's wrong, right? Remember, this is just a candidate. Well, this is always between 0 and pi, or 0 and 180 degrees, right? Every angle here has to be less than 180 degrees. It's a triangle, right? The angles add up to 180. So you're dealing with something that's a triangle. The inverses always give you exactly what you need. It's not going to give you the other one. All right, here's one. We know the opposite side and the hypotenuse. Fine. Sine is opposite over hypotenuse. The theta is sine inverse of 610. Plug that in your calculator and it's going to give you an angle in radians. When do you get your x back? Right. When do we get our x back? Right. Remember, we want this to just undo one another. But it can't always work, right? Remember, if you did the square root of minus 2 squared, this is 4. I'm sorry, not 4. This is 2, not minus 2, right? You're not getting your number back because the square root isn't perfectly invertible. It's invertible in the restricted domain. So these ones where the inverse is on the inside, hey, it's no problem at all. The inverse can only deal with stuff that comes out of sine. So sine inverse, you can only plug in minus 1 to 1 into sine inverse. Anything else, I have no idea what you're talking about, right? It was invented to clean up after sine, and sine always leaves stuff between minus 1 and 1. Well, that's exactly what comes out of sine. So the only things we can plug into sine inverse is exactly what comes out of sine. So you will always get your x back, okay? You'll always get your x back as long as it's defined, right? You can't plug in 7 into sine inverse. It goes, I have no idea. 7 isn't something that ever comes out of sine, so it's not something you could plug into sine inverse. So as long as the function is, if this is defined, you're going to get your number back, right? Same thing with the cosine inverse. This guy can only accept these numbers, right? It spits something out, and cosine always gives you something between minus 1 and 1. So as long as it's defined, you're going to get your x back. Same thing with tangent inverse. It's these doohickeys here where you have an issue, okay? So sine, you can plug in any real number you want, right? But sine inverse can't give us any real number. Sine inverse can only give us something between minus pi over 2 and pi over 2. So the only time you're going to get your actual x back is when this is what you're plugging in, okay? Think about it. If you can put an a, b, a c, and a d into a function, but it can only give you back a's, when do you get the same thing back that you put in? Well, it better be an a that you plug in if you're going to get an a back. All you can get back is the letter a. Put a b in there, you're not going to get an a back. Yes. Yes. Yeah. So like for sine here, you can plug in any number you want into sine. It spits something out between -1 and 1. We know that, right? That's what can go into sine inverse, right? Yeah, plug that into your calculator. It's going to go error. Yeah. And this guy always comes out with something between minus pi over 2 and pi over 2. Okay. So yeah, if that's what you're plugging in, that's what you're going to get back, right? But if you plug in something else, you're not going to get it. So for example, cosine of minus pi over 4. Let's see, cosine inverse of cosine, right? Well, cosine of minus pi over 4 is, I shouldn't do that again. I should do 3 pi over 4. No, yeah, that'll work. Minus pi over 4. Cosine of minus pi over 4 is root 2 over 2. So here's minus pi over 4. This guy has no idea about this angle. This guy, all it's seeing is root 2 over 2. It doesn't know where it came from. Has no idea. It says, oh, it must have come from here. Right? We're not getting the same number back. Right? This is a fancy way of writing root 2 over 2. Yeah, we see that it came from minus pi over 4. But mathematically, this is just a fancy way of writing that. And this thing here is not reading our handwriting. It's only seeing the values. It doesn't know where it came from. It gives us a candidate. It says, yeah, pi over 4. They have the same x value, right? Root 2 over 2. They have the same x value. So it doesn't know. So that's how you know whenever you're going to get your x's back and when you're going to get something related, right? Right? These two numbers are related because cosine of both of them is root 2 over 2, all right? Blah, blah, blah. Let's look at some examples. Sine inverse of sine of pi over 3, right? Well, this angle pi over 3, where is that? It's right up there, right? It's between minus pi over 2 and pi over 2. That's an angle that can come out of sine inverse, so we know it's just going to be pi over 3. However, this guy, this 2 pi over 3, where is that dude at? It's over here, right? Well, sine inverse is always going to give you something over there, so we know this is not going to be 2 pi over 3. It can't. That number cannot come out of sine inverse. All right. But it turns out that this angle here, pi over 3, sine of pi over 3 happens to be the same as sine of 2 pi over 3, okay, because of symmetry. So instead of getting the 2 pi over 3, it's going to give us this one instead. Now these two angles are related because sine of either one of them, right, they're going to be equal, but you're not going to get your original number back. Here's cosine inverse of cosine. Where is this 2 pi over 3? All right, we already drew it. There's our 2 pi over 3, right? Well, cosine inverse always gives us something up here. Well, that is up there. Fine, we get our 2 pi over 3 back. However, minus pi over 3 is down here, but cosine inverse always gives us something up there. So instead, it's going to give us that one. It's going to give us pi over 3, because cosine of both of those is what, a half, right? So you're not going to get the minus pi over 3 back. And here's a trick you could do. This is equal to, cosine is an even function. Even functions, you can throw the minus sign away, right? So all I did was I threw that minus sign away. Now that is up here, so I would get my number right back. So you can use your identities to finagle the angle in there, right? Using identities. The cofunction identity is useful for that. Let's look at tangent here. Remember, tangent is pi periodic. Okay, so here we have pi over 8. Well, where's pi over 8? It's like right here. Tangent inverse always gives us something over here, so we're going to be like, yeah, pi over 8, boom. But this guy, 11 pi over 9, let's see, there's 9 pi over 9, 10, 11. Well, tangent inverse always gives us something over there. That's not over there. Tangent's pi periodic. Tangent inverse is going to give us this angle instead. So what is that? Well, if this is 11 pi over 9, this would have to be a 2 pi over 9, right? We'd have to subtract off 9 pi's over 9. So you could use the periodicity of tangent, right? 11 pi over 9. I can always subtract off pi from the angle and maintain equality, right? Because tangent is pi periodic. Tangent inverse of tangent. 11 pi over 9, let's see. Pi is the same thing as 9 pi over 9. 11 minus 9 is 2. Okay, and this is right here. Tangent inverse is happy to give me anything over there, so I just get the 2 pi over 9 back. Just using the periodicity of tangent, it's pi periodic, right? Tangent inverse cannot give me that angle. It's going to give me a representative from over here. Cofunction identities. So sometimes they like to mess with your head. They give you stuff that doesn't match. All right, not the same. Well, remember your cofunction identities. Trig of theta is identically cotrig of 90 degrees minus theta. You can always do the switcheroo here. So this guy, let's replace the cosine with sine, in which case we have to change the angle to its, what is it called, complementary angle. So I'm just using this. I'm replacing cosine with sine of 90 minus that angle. So let's see, if I'm going to add, let's see, I multiply the top and the bottom by 3. Okay. This is sine inverse of sine. 3 pi minus 13 pi is negative 10 pi over 6. I can reduce this fraction. Divide the top and the bottom by 2. Right? Yeah, just reduce the fraction. So I wish these would just undo one another. Well, where is this angle at? Minus 5 pi over 3. Let's see, 3 pi over 3, 4 pi over... There's minus 5 pi over 3. Well, sine inverse is not going to give me this angle, right? Sine inverse gives me something over here. It's going to give me this angle, which is pi over 3. Okay, so I did the switcherooski, switch the cosine to sine, but that still wasn't enough just to give me this back, right? I started to think a little bit. It's not going to give me that. Sine inverse always gives me something between here and here. Do one more. We can do it. All right, cosine inverse of sine. Let's turn the sine into a cosine. So this is cosine inverse of sine. No, change the cosine into a cosine. We need to do pi over 2 minus a negative. So I switch from sine to cosine, switch the angle. What are these? Let's see if I multiply the top and the bottom by 2. 2 and 11 is 13 pi over 4. All right, where's 13 pi over 4? Let's see, here is 8 pi over 4, 12, 13 pi over 4. Cosine inverse is never going to give me this angle, right? It's going to give me that angle. It's going to give me 3 pi over 4. It always gives me the one that's up here between 0 and pi. And cosine of this is the same as cosine of that. They have the same x coordinate. So that's how you do it, all right? The next time we're going to make it even more complicated. All right, so practice, practice, practice. All right.